Let's say we have the following matrix. So it's a symmetric matrix. Okay. First we want to find the eigenvalues and eigenvectors. Okay. Then we want to find a orthonormal Eigenspace. Okay. And then we want to calculate the exponential, so e to the power of that matrix, which is equal to the limit as upper n goes to infinity of the sum to upper n from n equals 0 of 1 over n factorial times c to the nth power. Don't be afraid, it's really not that complicated. You will see why. So first we'll find the eigenvalues of that matrix. So we have to calculate the determinant of c minus lambda times the identity matrix is equal to 0. Okay, so we have to do the following. So we have to find the determinant of that thing. And so if you calculate the determinant, you will get that, so this has to be 0, so you will get that 2 minus lambda times lambda squared minus 4 lambda minus 5 equals 0. And so then 2 minus lambda times lambda minus 5 times lambda plus 1 equals 0. Okay? And so our eigenvalues are lambda 1 equals 2, lambda 2 equals 5, and lambda 3 equals minus 1. Okay? Now let's find the eigenvector for lambda 1. So we'll get the matrix, so 2 minus 2, 0, minus 3, 0, 2 minus 2, 0, minus 3, 0, 2. That is equal to 0, 0, 0. So here we get 0, here 2, and sorry, I forgot 2 minus 2. Here I get 0, 2. Okay, so I get that minus 3 x3 is equal to 0 and minus 3 x1 is equal to 0. So I get that x1 equals x3 equals 0. Okay, and x2 is 3. Okay, because you have 0 times x2 equals 0, so x2 can be everything. And so we can find some vector. Let's say you call it v1, which is equal to 0, 1, 0. Okay, because you only have a free coordinate in the x2 component. and it can be everything because x2 is 3. Now let's do it for lambda 2 equals 5. So we get that 2 minus 5, 0, minus 3, 0, 2 minus 5, 0, minus 3, 0, 2 minus 5 is equal to 0. So you get that so this gives negative 3, and this also. If you row reduce, so if you subtract row 1 to row 3, basically you get minus 3, 0, minus 3, 0, minus 3, 0, 0, 0, 0. Okay? And so you see that x3 is 3. Okay? x2 equals 0 and x1 is equal to minus x3. Okay, you divide here, you divide by negative 3 on the first row, then you subtract x3 and you get that x1 equals negative x3. So our second eigenvector, let's call it v2, is equal to, so x2 is 0, let's take negative 1 for x3, and so x1 will be 1. Okay. Now we do it for lambda 3, because negative 1. Okay. So if you do the computation, you will get that the following matrix, if you already eliminate the third row. Okay, and so you get that x3 is 3, x2 equals 0 again, and x1 equals x3. Okay, so you get, for example, that v3 equals 1, 0, 1. Okay, so we have our 3 eigenvectors. So so v1 equals 0, 1, 0, v2 equals okay, and v3 equals 1, 0, 1. Okay. So we have found our eigenvalues. So let's just recall 2, 5, and negative 1. And we have found the eigenvectors. Now let's go to B. We have to find an orthonormal eigenbasis. Yeah, we have to find an orthonormal eigenbasis for the eigenspace. So, orthonormal eigenbasis for eigenspace. Okay, And so here we will do a trick. We know that C is symmetric. Okay. Let's just this is C. You will see this is symmetric. And you have a theorem that states that the eigenvectors of a symmetric matrix are always orthogonal. Now we just have to make them length 1. Okay, so our first vector of the eigenbasis will be v1 divided by its length. The same for e2 is equal to v2 divided by its length, and the same for e3 is v3 divided by its length. Okay, so let's do that. So basically our first vector is already the same. Okay, you will get the same vector because it will be divided by the square root of 1 squared, which is 1, so you divide by 1, so it doesn't change anything. v2 will be for v2 we'll get 1 over square root of 2 times 1, 0, negative 1. And for v3 we will get, so e3 1 over square root of 2. Okay, so this is our orthonormal eigenbasis. Now let's do C. So our third question was, we have to calculate e to the c power equals this strange thing. So don't be afraid, it's really not that complicated. Sorry. Okay. First, what we can do is we can express our matrix C in, we can diagonalize it. Okay, we can express it in the product of matrix T, D, and T inverse, where D is a diagonal matrix and its entries are the eigenvalues of C. So you can put them in whatever order you want. 2, 5, negative 1. So it will be 2, 5, and negative 1. Okay? And T, basically, these are the orthonormal eigenvectors. So we'll take E1, E2, and E3. Okay? So we will get 1 over square root of 2, negative 1 over square root of 2, okay, and because this is an orthogonal matrix, so the vectors in this matrix, they are orthogonal, remember. So it's an orthogonal matrix, and we know that the inverse of an orthogonal matrix is equal to its transpose. Okay, so we just have to transpose that, and we will get our matrix T inverse. Okay, so you just take this transpose. Yeah. And now, basically, if you calculate e to the c power is equal to that strange thing, so limit of upper n goes to infinity of the sum n equals 0 to big N, 1 over n factorial times c to the n. if you substitute C with T, D, T inverse, you get that this is equal to the following. The sum 1 over n factorial times T D T inverse to the nth power, okay? And if you put that in this form, basically the nth will only affect the d, okay? You will get the same thing, but here you will get T, D to the nth and T inverse, okay? Because T and T inverse are orthonormal matrices, okay? And T is diagonal matrix, okay? So if you take it to the nth power, it will only affect D and yeah, okay? And then you can rewrite it as T times the limit as upper n goes to infinity of d to the n T inverse, okay? And this is equal to T times basically what is here, that's just e to the t power, then times T inverse, okay? Okay, remember that's the same thing as T beginning, okay? And now basically e to the t power, D is a diagonal matrix, so it will just be e to the raised to the power of the first element of our diagonal matrix. Remember that the diagonal matrix, its elements, its non-zero elements are the eigenvalues. So it will be e to the 2 power, e to the 5 power, and e to the negative 1 power. Okay? And so you can write that e to the c power is equal to t times e to the d times t inverse. Okay? We know t. We know its inverse, which is its transpose. And we know e to the d. So you can calculate that, you can compute that, and you can find e to the c power. Okay? Yeah, if you do it right, you should finally get 5 plus e to the negative 1 over 2, 0, over 2, over 2. Okay, you should get that. It's just computation. We know T inverse, which is T transpose, we know T, we know e to the t, and so you can calculate that. Thanks for watching.